Okay, welcome back, everybody. It's time to start. So let's get started with Yang's final lecture. Okay, so welcome back, everybody. This is Yang's final lecture, so it's time to get started. So over to you, Yang.
Okay. Thank you very much. So let me just, I just want to emphasize, so my last lecture, I gave an overview about machine learning and emphasized on neural networks and methods of testing: one, precision, naive precision, and two, how would you do confidence in terms of categorical classification and in terms of regression as well. So I just want to emphasize one. I mean, I told you there, I divided, it goes into supervised and supervised learning. There's another one, which is sort of my favorite thing, and that's not a neural network, and it's so-called support vector machine, which I'm going to use. I'll mention later on. I like this one because the biggest problem with neural networks is interpretability, right? Because there's so many parameters and hyperparameters, it's very, very difficult to know exactly what's going on. Support vector machines is it's a very simple concept. I have a giant point cloud of data, and I labeled it, in a certain way. And the support vector machine is an optimization problem which finds hyperplanes of separation. Okay, that's all there it is. So, for example, in a binary classification problem, so this is a labeled point cloud of data, where y is just plus minus 1. So the blacks are plus 1 and the whites are minus 1, say. It's two categorical. So this is a binary classifier. And what the support vector machine is to find a plane which optimally separates the two. So that's the hyperplane which separates these two data. This is extremely interpretable because that's just two sets of data, right? The matrix of weights and the shift vector. So it's essentially n squared plus n parameters that you can just literally see, right? And so just very briefly, this is an optimization problem, and you just find the minimum of the distance that this plane is from one point cloud and from the other. You can just keep on shifting this until you find the maximum. So under this constraint. So this is again some Lagrange multiplier, and you can find these weights and biases according to this way. So I want to emphasize support vector machines because it's sort of become one of my favorite classifiers, because a neural binary classifier has so many things, there's so many layers, you don't know what's going on, but this you can actually give the equation of separation. Right. And in the case that the hyperplane is, you can even do a little more sophisticated stuff. It doesn't have to be a straight plane, of course. You can be a hypersurface. So that's in machine learning, this is called the kernel trick. But all that means, for us, it's just a fudge factor, which could be nonlinear, and you can separate it by some other means that distorts this hypersurface. So I won't get into the technicalities of regularization, but I just want to say there's some technical jargon that I want to say. During the training of a neural network, so there are things called a training round or an epoch. I'm going to use this in an example shortly, so that's going to, it will illustrate all of the things I'm talking about. So this is one complete cycle where your neural network has seen the training set. So this squiggly T is my training set. And so that's the epoch. Sometimes, of course, most of the time, in fact, your training set is too large, right? So you want to feed this into your laptop. So you want to do what's called batching or mini batching. So you just divide your training set in little bits so that your neural network will only see little bits at a time. And then you go through all of the training set in terms of iterations through these batches. So your training size is batch size times the number of iterations. Okay, so, and you often want to sample sometimes you want to sample through the training set through this, remember what I mentioned, this stochastic gradient descent, in order to randomly sample through your batch size, and you want to pass through multiple training rounds or epochs of your training. Okay, so I'm going to illustrate this in a minute. So, so back to neural networks. I won't get into any of these details. So I think that's a bit too boring. So now it's clear what we need to do in some sense, right? Because we've got a lot of data that's been gathered in the last 40 years, since the mid-80s, are pure geometry data, which very interestingly was done for the sake of string theory, but it just so happens this way. But this data is interesting in and of itself. And 40 years of data and the last 5 to 10 years of sort of personally available GPU units to process that data through machine learning. So it's only natural that you put the two together, and that's what I was trying to do when I said in 2017. The question I was asking is precisely this, right? So can you process this data in a meaningful way? And so remember, you can use all these neural networks. Usually for image processing, you use what's known as a convolutional network, but I won't get into that. And then you just try to process image recognition problems of such a type, right? So let's go ahead and do it. Let's start with the simplest data set in Calabi-Yau manifolds, or actually it's the simplest data set in string theory, which is the hypersurfaces in weighted projective 4, right? So remember what the data structure was. You have a 5-vector input in terms of the weights. And say, for example, you want to classify the H11 of such a data set. Okay, so so my student Ed and Jacon will give a tutorial of how to do this whole stuff on Keras, on TensorFlow, Python's TensorFlow and Keras, and it will give you during the tutorial they'll give you sort of an illustration of what it's like to play around in such an environment. A lot of the code, as I said, is again given in my book, but I thought I would just want to take a few moments to demonstrate on Mathematica, because I think this audience is very I don't know, heavily Mathematica biased. So I'm going to just use this very simple data set to illustrate the kind of things that you can do with Mathematica 11 version 11 plus. So now we're at 11, we're Mathematica version 13. So let me try to share. So this is where I was telling Aninda we keep our fingers crossed, because live coding is always a very dangerous thing. All sorts of things can go wrong. So let me pull up, and I will email out the this demo package together with the data so that everybody can see. So I'm opening up Mathematica, and I think I can share it with you guys. So can everybody see my screen now?
Yes. Okay,
good. So here I'm defining again what a Matthews coefficient. I'm defining the confusion matrix. These are built into classifiers, but I just, it's simple enough to code up. That's it. It's just half a page of code, and that's okay. This is just to define some of the parameters that we will actually use. Okay, so here is the meat of the project. So I'm going to read in the data of this is again this data of weighted projective space is available on the KAWS database. The link is in the slides, so you can just download it. But I put it into Mathematica format because it's kind of nice. So you can see what a typical entry of this looks like in terms of this data. So this is the first one, right? So this is the way to read. So what it is, this is weight 1, 1, 1, 1, 1. So it's weighted projective space with all trivial weights. Therefore, the ambient space is just the regular CP4. Great. So the only Calabi-Yau manifold, which is the hypersurface in regular CP4, is just the quintic. So this is the quintic. So the quintic is now just the input 1, 1, 1, 1, 1, 1. It has Euler number -200. It has H11, 1, and H21, 101. You can check 1 minus 101 times 2 is -200. So that's this typical data, right? The next one is, whatever, this is weight, you put 2 weights on one of them. So this was classified by Candela's, Linker, Schmerink, and friends. And it comes down to about as I said, 7,555 cases, right? So this is a very simple structure. And you can see, here's the distribution of H11. You just do a histogram, and you can see it's Planck. Here's the histogram of H21, it's also Planck. And the distribution of the Euler number, which is roughly Gaussian, but we know secretly it's not. It's sort of this pseudo-void plus a Gaussian deformation kind of distribution. The peak, again, is at the self-mirror manifolds of Euler number 0. Okay, so that's all good. Now, here's the key part. You want to create a labeled data set. Now, I'm going to make life easy. So I know you can see that H11 ranges from, this is H11, it ranges from 0 to around about 300. So it's a quite large span. And let me just ask a very simple binary classifier just to make our lives easier for this demonstration. I'm going to ask, can a neural network recognize when something has large Kähler structure? So I'm going to call large something bigger than 50, and I'm going to call small something less than 50. I chose 50 just because it's more or less the same, more or less the equal amount of bigger than 50. You don't want it to be too unbalanced, because if I chose everything to be, if I chose like large Kähler structure to 250, that there aren't that many of them, and your neural network can get pretty high precision, but just simply guessing that everything has very large, everything has very low Kähler structure H11. And of course, even in such a case, this is why we need to do precision and confidence tests, because the confidence, even in those cases, the confidence confusion matrix will show that it's not as diagonal as you wish. But I'm going to make a binary classification of H11 bigger than 50 versus H11 less than 50, bigger than or equal to 50 or less than 50. So I create this database. So the way to label it in Mathematica is through the arrow. This is very specific to the Mathematica syntax for neural networks. So I'm just saying that if it's greater than 50, I'm going to call that a 1. If less than 50, it's called a 0. So here now I've created a labeled data set of 7,550 cases of just 5 vectors being labeled by 0 or 1. So now I have a binary labeled data. You can see the input feature it gets pretty wild later, right? So you can, with the coprime integers, it's a 5 vector of coprime integers, but it is what it is, right? The point is, I can't just look at one of these and say, well, oh yeah, this is a 0 versus something that's kind of wild that's not a 0. For example, this. I mean, of course, you can take your favorite data set and do whatever you want, but this I just want to illustrate the syntax here more than anything else. And you can see that there are about 3,000 zeros and 4,000 ones in some randomly mixed up fashion. So now I'm going to do. As I said, I'm going to split my data into training set, test set, and validation set. So the training set is a random sample of 2,000 cases from the 8,000. Okay. The typical numbers in machine learning is what's called a five-fold validation. What that means, you take your full data, divide into 5 batches of 20% each, and then you sample through all permutations of choices of 4, and you train through the 80% and you validate on the 20%. Okay, so that's what's called the five-fold validation. I'm going to do something more extreme just to show how well it behaves. I'm only going to feed in 20% of the data, so you will have only seen 20% of the random sample around about 8,000 cases, and I'm going to actually test it against. So it's extremely important to use complement, because you don't want your neural network to see something it's already seen, just in case of any overfitting. So you take the complement of the 2,000, that's still around about 80%. So I'm going to train on the 20%, and I'm going to validate on the 80%. And then, as I said, during training, you want to use what's known as a validation set, not the test set you want to do after you've made your neural network rigid. And during training, you want to test a small set of validation just to see how your training, how your loss function behaves in training. And you don't want that to be too big. I mean, for 8,000, it doesn't really matter because there's just so much your machine is so good, as you'll see, that it doesn't matter. But in case if you're training into the millions, you don't want your in-training validation set to be in the hundreds of thousands, because it's going to slow the training process down. But you can see that you can visualize this very well during training process. Okay, so
Yang, one quick question about so the second line, shouldn't the second entry be training set and not training? So can you just clarify that?
I'm sorry.
Because you called it your complement DDD, the second entry, should that be training set? Because you called the.
Oh yeah. Sorry. Very good. Yeah, good. Thank you. Sorry. Yeah. Yes. Absolutely. Thank you. Good. I'm glad everybody's paying attention. Yes. Thank you. I'm just going to give you a second. Thank you. I'm glad. Yeah, it would have gone wrong. So let me just do this. Whoops, sorry, I didn't do DDD. Sorry, my DDD. Yeah, my DD. I haven't defined my DDD yet. This is my DDD, and you can see this. And then I'm gonna do the sample. Right. So here you can clearly see. Whoops. So your training set has size 2000, and your validation set has size 500, and your test set has length much bigger. I'm doing something very ambitious because I'm training a minority and testing a majority, right? Of stuff that he has not seen. So now I'm going to establish two different network architectures. If I can find my, my window demo. Yeah, there we go. So as I said, this is a discrete problem. So I'm going to use a classifier, a categorical classifier, and I will use neural networks in both cases. You can use support vector machines or any of the other stuff. I just want to, they're much easier. So I'm going to use the neural network, and I'm going to use the feed-forward neural network. I'm going to illustrate it first with the classifier, and then I'm going to classify. Then I'm going to turn the question into a regressor problem. I pretend, that I can extrapolate through some kind of sigmoid function, and I'm going to take the integer round of that to see the 0 or 1, right? So this is a problem of 0 or 1. So you can see the architecture of my neural network. See, the command to use is net chain in Mathematica, and a net chain. There are more sophisticated things called net graph, where you can have more, where you have different interconnectivity according to a graph structure. But here, because it's a feed-forward neural network, I'm just going to see explicitly in forward feeding layers. The universal approximation theorem says that this should do anything. This should do, as long as you have enough number of layers and enough width, you can approximate anything. So can we do that? But I'm going to choose something very, very simple. I'm going to choose something that only has 3 hidden layers and 1 input layer and one output layer. That's it. So this is an almost embarrassingly simple neural network. It has 5 layers, and that's it. So the universal approximation theorem should not even apply to this, right? Because this is just a very simple thing. And I specify here, and you can twiddle around with this, that the input is a 5 vector. So that's hence the curly bracket. The output, now here is something that needs a little bit of fiddling. The way to read it is that you don't actually have to specify it, but sometimes, I don't know, sometimes just from experience, it goes wrong if you don't specify input and output, because you can't let Mathematica do everything. The output is the net decoder. What this command does is to explicitly tell the machine learning algorithm that you want to encode your output into a classification problem, that's class, and the classes are just between 0 and 1. Okay, so that's all there is. So it's a categorical classification of zero, a binary classifier. So linear layer means it's fully connected, a fully connected affine transformation. So that's the identity activation function. With weights and biases, it becomes the general matrix affine transformation. The second layer I put in is a element-wise layer of logistic sigmoid function. I can play around. ReLU would be fine too, possibly. And I'm going to follow that up with a hyperbolic tangent. And then I'm going to make it into a fully connected binary layer, hence the linear layer 2. And so at this point, it will output something between 0 and 1, right? Some number, right? Because these affine transformations up to this point will be some real number between 0 and 1, a pair between 0 and 1, right? The two classes, both of which are 0 and 1. I'm going to take a softmax layer, which, remember, the softmax is one that actually I can, that takes, I wish I could, give me 1 second. I will try to share both my screens just to make life easier. Share my everything. So now you should be able to see both, right? Is that, can you see both my screens?
Yes.
Okay, now you probably should see yourselves as well. So remember here, these are the functions I'm going to use. I can play around with it. Sigmoid, so the softmax is this sort of a smoothened out maximum. You try something else if you want. So that's it. What you can, a wonderful thing you can use is called the information, information command, which plots for you. So the information command will tell you everything about net. In fact, the information command is a new command that's existed since Mathematica 12.0 plus. It gives you information about any structure, but in particular, it gives you structure about this network, and the full summary graphic gives you actually the structure of this forward-feeding neural network. So this is the linear layer of 100, the input 5 vector 100, followed by element-wise logistic sigmoid of the 100, followed by hyperbolic tangent. You can remove if you want, and then the 100 will be moved by an affine transformation to 2, and then a softmax into a 2 vector here, and now it splits out the vector. So this is a 5-layer feed-forward neural network of such a type. It's very nice. It's got a summary graphic. So that's it. My network is done. My training set, validation set, and test sets have all been established. At this point, the magic command is called net train. This is what I love about Mathematica, right? It's very high level, so everything's in there. So let's see what we're doing. The net train says, I'm going to train the network that I've established here with my training set. I will retain all of the information. So now everything's optional. My in-training validation set is that small validation set I just want to see. And the method I'm going to use, so the learning rate, remember, is the stochastic gradient descent parameter. Just see how fast I'm going, zooming in finding all of the minima. And then there's an optimizer called Adam, which is what everybody uses. Frankly, I have no idea what it is, but now this is very high level machine learning, but as far as I know, everybody uses the Adam optimizer during training. It optimizes certain searches for minima. And it's not even named after somebody called Adam. So then again, I said the training rounds is 100. So that's my epoch as I feed into, remember my training rounds in this jargon is the number of times, it's the number of iterations I'm going to go through my training set. So my training set is 2000. So I'm going to go through 20 epochs, right? Again, this is a categorical classification problem. So I can specify my loss function to be the cross entropy loss function, which I said, for categorical classifiers, your loss function is typically chosen here. If you have a discrete problem, you choose this as your cross entropy, right? Where D is the label and X is the input. So your X is the 5 vector, your D is either 1 or 0, and you use this cross entropy. The index is to tell it, I don't know why you need this extra thing, but the index tells it that it's an index type of cross entropy, that it's a categorical problem. So let's do it. Let's train this neural network with our data. So you can see it's very nice. It's in training. You can see it takes. So you can see the whoa. So that was too fast, right? See, this is how fast we're doing. You just processed 2,000 training sets in under like 3 seconds. But it's so fast I may want to do it again. You can see how you want to see the loss and error rate to be in this shape. If it's not doing this, we can look at the loss rates. And if it's not doing this in training, you're doing something wrong. And it's plotting the orange and the blue to show both the validation on the training set and the validation on the the validation set to see how they're both going down. So if the validation loss is if the loss on the training set is going down, but the validation set is not going down, then that's very much indicative of overtraining. You're doing very well on what you've seen, but you're not doing very well on what you've not seen. So that's a typical case of overtraining. Okay, let's do it again. It's so quick that you can see, you can keep track of all of this, and you can see that it's going to go through some 20 iterations of batch size 100. So that's it, it's done. That took 3 seconds. So this is why it's so wonderful. This could not have been done 10 years ago, right? Your personal computer would not be able to process 8,000 data points in under 3 seconds in this way. And the number of parameters is there are a lot of hyperparameters. Again, information will keep track of all the hyperparameters. If you really want to get into the under the hood, you can track everything, and you can get full information on that. So it is done. So now the next thing you do is you take this net full, which is this fully trained neural network, and I'm going to extract the information called the trained net. So that means I want to extract out the trained network, and I want to validate that. That's my, this is going to be my function. It's a very complicated function, but it is what it is. So what I'm going to do now is I'm going to extract out this bit, which I'm going to call trained NN, which is the trained neural network I'm actually going to use for my function. So now I'm done. I can now take my test set, which is what I said, there's the training, in-training validation, and the test set. Here is the vast majority of things I've not seen. This is about 5,000 cases. And I extracted out the 0 and 1 values for those, right? So here's just a 5,000 length vector of zeros and ones. Now, okay, that's just data processing. This bit is the key. I'm now going to use my trained neural network and evaluate on the 5, so this is the 1, on the test set 5 vectors, and let me see what it actually predicts. Okay, so, and you can see now it's going to actually evaluate see, that took under 2 seconds, and it's done, which is wonderful. So you can see that my actual, so just to give you, just to remember what we're doing. So my test set is of something that looks like this, right? I'm just going to evaluate on stuff look like this. My actual is a set of zeros and ones, right? It's pretty randomly distributed. There's a bunch of zeros, a bunch of ones. And this is in sequence. Of course, everything's shuffled up. I'm constantly shuffling random sampling, so I don't introduce any bias. And then my predicted one is again a sample of some ones and zeros and ones. So I want to check this vector with this vector. And so I can do that. So that allows me to evaluate naive precision. And what that is, I just simply select the number of cases where the difference of the 2 5 vectors are equal and I count its length. Okay, and divided by the length of the actual, divided by the full. So if you evaluate this, you get a point. Of course, this number changes, right? Depends on, you get 94% naive precision. That's pretty good, right? It took 6 seconds, 3 seconds for training, 3 seconds for the full validation, using a 5-layer feed-forward neural network on something that a calculation for which is actually quite difficult, right? The Euler number, even the Euler number, there's an analytic formula for the Euler number. It's like a huge sum, and it's like all over the place. And the individual H11s, H21, back in the day, Candela's friends had to actually use, very sophisticated Landau-Ginzburg methods to evaluate. But thank God they've evaluated for us when we're just checking this, and we got 94%. That's really wonderful, right? And it's not good enough, right? We want precision and confidence. So the confidence level is given. Sorry, the confusion matrix, right? So here is how many cases that are true positives, true negatives, false positives, and false negatives, right? So you want this matrix to be as diagonal as possible, and it's true, and it's pretty good. So, I mean, of course, there's some mistakes. It's misclassified on the order of hundreds in the case of orders of thousands. So the Matthews coefficient, the Matthews phi coefficient, it checks a sort of the chi-square of this contingency table, and it's about 0.9. So it's fairly close to 1, right? So that's So this is what a typical calculation would involve. So I think, take your favorite example and start just playing with it, right? If you want to, of course, I've only used a binary classifier, and the actual H1 ones are much bigger, and you can do that, and then you can make that into a 100-way classification problem. So your confusion matrix will be 100 by 100. So together with Dave Berman and my student Ed, we just did this last month of a much more serious analysis of the 7,000 cases. And I think Ed will tell you that in tutorial, and mainly to illustrate how this can be redone through TensorFlow's implementation. Okay, so that was fun. Now I'm gonna let me just finish off by saying, well, that was a binary classifier that I used, but what about a regressor? Let's pretend that the problem is continuous, and let's see whether I can take the integer round and see if I can do any better or worse, right? So again, I'm going to use roughly the same architecture of the neural network. My input now is the 5-vector, and I'm going to use a summation layer, which takes the last linear layer. I'm going to sum it up to be some integer between some real number between 0 and 1. So again, it's a feed-forward network of these layers. Okay, so let's try this one. This is a regressor, and that's what it looks like. And I'm going to now, because this is a regression, a regressor type of thing, it is more customary to use mean squared loss instead of cross entropy loss. So mix it all up and play with it, right? So we're going to use the standard deviation, the squared of the standard deviation in regression type analysis. Of course, you feed this into a linear regression, it's just not going to work. Right? There's no way you're going to predict linear regression out of this five component for something like this. And that's so this is the magic of connectivity, right? Because you have a more sophisticated approximator. So here, let's do it again. You should take under 3 seconds. You can see the loss of your mean square of your mean square layer. And you can see the validation loss is getting very good, right? And then it goes down. And then again, you do training and prediction. And that should take in about 3 seconds. And here, because your actual is the same, but your predictions are different, right? Because I said this is a regressor. So your predictions are some real numbers. I think between -1 and 1 or something, between 0 and between whatever. And then what you do, of course, is to take the integer round of this and do the comparison, right? And you also get about 94%. Surprisingly, this problem is just as good being had you not known that Hodge numbers were not integers, this problem would have been just as well approximated by this regressor neural network. And the math is fine. Again, it's around about 0.9, and your confusion matrix is also very good, right? So are there any questions? I hope this demonstrates that how nice it is Mathematica has made life for us. Any questions? Everybody's happy?
Yeah, I don't see any questions.
Okay, good. So I hope that was clear. That was fun, right? Yeah?
Yeah.
I was hoping one of the students would say, yes, that was fun. Okay, so that was so easy, right? It was under 2 pages of code. It's like nothing. And
somebody has agreed with you that it was fun in the chat box.
Okay, good. Yes, it was fun. Good. I'm glad we had fun. So now the proposition. Now let's back to some generalities about this whole story. Let me try to share it again to. Sorry, I'm going to share my slides again. Share slides. This one and just control full screen. Yeah. So as I said, we recently did a more serious analysis of this, and Ed did. So Ed Hirst is my my PhD student, and he did a wonderful job at doing some serious TensorFlow analysis of this. And I think we'll talk about this in the tutorial. So the input feature of that was very, very simple. It was just a 5-vector. So right, but remember, SISSEs are matrices, right? So you can make this a little even more colorful, right? Because remember, SISSEs are matrices of certain size, right? So if you pad with zeros, a SISSE, a complete intersection Clavier manifold, is a 12 by 15, 6-colored pixelated image. In some sense, this is what got me thinking about this whole problem in the first place. Because Mathematica had this wonderful command called array plot. It plots arrays for you. So this is the array plot for SISSE. When I plotted something like this, it started reminding me of this problem. Right? Here is the letter 3, the number 3, and I want some kind of machine learning algorithm to recognize that 3 is 3. So how different is this recognizing this image to be some typical Hodge number, right? When I first tried this, I didn't think this was possible because, integer, hand digit recognition problem, we almost know it has to work, right? Because, people don't write 3s in crazy ways. There's a little bit of variation. And you can, this is why Google works. It's because human beings don't do crazy things. But what about this is pure mathematics. The data here is very rigid, and how do you recognize this image to be something that a very sophisticated set of algorithms is actually computing, right? So so you just try it, and that one worked. The original one that I did in 2017 was a binary classifier of this type, and since then I did this with my friends, of course, Vishnu and Challenger, and also my master student Kieran Bull, who is my master. This guy is awesome. Kieran Bull, he was my master student at Oxford, and this guy is like he eats 7,000 lines of Python for breakfast, and he essentially taught me how to use things like TensorFlow. So he made this into comparisons between support vector machine classifiers, neural net regressors, and neural net classifiers, just like you think, but in a 20-way classifier, right? Because my H11s go from 0 to 19, and we're not just doing simple classification estimates, but we actually want to get the H11 value, and you can see that so this is the learning curve. So this is different from the training curve. The training curve is typically in training, how does your loss function behave? And you want that to decrease. The learning curve is how much naive accuracy you can get as you increase the fraction of your data used for training. So it was at 20%, it was actually struggling a bit. You got 70% accuracy. But as you go up to 80% accuracy, 80% training, it's very quickly getting up to the 90s. And again, this was we were using support vector machines that I introduced earlier, a neural regressor, and a neural classifier. So the best one that performs well is actually a neural net classifier. And since then, this has been massively improved over the last years, especially by various friends of ours. So Sven, and then then I started doing stuff with Andre Lucas and Magdalena Larfos, and also Urban and Finatello. These guys used a very sophisticated neural network called the Inception, the Google Inception convolutional network. So this is what this network structure. I won't bore you with. This is some big thing. You can read it in their paper, and this is what Google actually uses when it's recognizing your handwriting, right? So every time you write in your iPhone or your tablet, it's taking that data. I don't know how comfortable you feel about that data, but I'm fine. And these guys are almost getting 100% precision over the entirety of the H11 in prediction of H11s for SISSAs. So that's kind of surprising, right? Because I said to actually get H11 and H21, we go way back to when I started. How would you actually do it, right? It's a very sophisticated procedure, right? You got to go through all the sequence, and you got to induce a non-exact sequence in cohomology, and a lot of this has been coded into Sage Math and Macaulay too. But for simple cases, you can do this. But as I said, this algorithm, as is the case with every algorithm in algebraic geometry, it's double exponential because of the Grosvenor basis bottleneck. You can't beat it. It's not like linear systems where you can get away with n log n, but for algebraic geometry, the bottleneck is the Grosvenor basis, which takes exponential time. But but at the end of the day, you extract a number, and somehow your neural network, a very, very simple neural network that you saw, right, that took like 3 seconds to train, or on the order of minutes to train and validate, was guessing at extremely high precision for some reason. And I still don't know what it's actually doing, in the sense like, well, yeah, here's a function that approximates it. But what we can do, and I will get to this point a bit later. So, that got me thinking, well, is it just a special feature about Hodge numbers, right? That would be interesting, right? Maybe Hodge numbers is special, that it behaves very well under machine learning. But let's try something else, right? So let's try, what about recognition of whether something's elliptic fibered, right? And again, this one is a binary classifier problem. So I did this with Sungjay Lee, and very quickly you can see that we're struggling in the 20% range. But the error bars are introduced because we did multiple sampling. But around about 40, it was converging very quickly to 100%, right? So that's a completely different problem. In fact, this isn't even an open problem, because the analytic way to do this requires some Collard's conjecture, which hasn't been proven yet. But Collard's conjecture gives you a method of checking whether Clavier threefold is elliptically fibered. But again, we did this over the SISSA data set, and the Collard conjecture had been checked case by case by Laura Anderson, James Gray, and Sungjay Lee and friends. So we actually had access to that data set, and and this was also surprising, right? So two examples. That's kind of interesting. And since then, there have been a whole community just testing various things, in the geometry related to string theory, and they all tended to work, right? I want to emphasize these beautiful papers of Hashimoto, Halvorsen, de Mello-Koch, and Van Turin, which go sort of an increasing level of generalization of what is actually possible. So Hashimoto showed that ADS-CFT correspondence can be rephrased into a Boltzmann machine, which is again a type of unsupervised machine learning algorithm. Halvorsen wrote this very nice paper that QFT itself, appropriately defined, is a neural network, in the sense that there's some input feature and there's some output feature, and then all of QFT can be rephrased in this one. De Mello-Koch and friends rephrase neural network. The RG flow is a neural network. And Van Turin has this very ambitious thing that the entire universe is, in some sense, a computational neural network. So this it's kind of interesting. But so these are more philosophical points. But I want to have a take-home message of the first part of this last lecture. And it's the following. And I know this is a very specific statement. One, any algebraic variety can be represented as a tensor. Right? Probably not more than rank 3. Right? Whether you want to keep track of degree, in which case you have families of algebraic varieties, or you just want to keep track of the coefficients of definition of a polynomial, because all manifolds can be defined by algebraic varieties. Right, so I think this is part of Chow's theorem. and even embedded into appropriate toric varieties or projective space. So what we're doing here is something very, very general. So here is sort of my, so I've gone a bit fanatic about this, which is the statement that computations in algebraic geometry is an image recognition problem, appropriately defined, right? No different. I mean, okay, so we know in principle how to get from this problem and compute it. And this is what the entirety of the Grothendieck, Bourbaki school did for us. Leray and all these people taught us how to reduce problems in geometry to this algebraic language. Of course, Grothendieck never went ahead and he probably never went ahead and actually computed anything. But since in the last 20 to 30 years, there's been an entire field called computational algebraic geometry, which takes the sophisticated language of the Bourbaki school and just started coding it into SageMath. So this is what made possible to create these databases. And if you look at these databases, it's an image processing problem, precisely because all of the input features is some kind of tensor. Not necessarily, it's an integer tensor if you just want to keep degree, and it's some complex tensor or real tensor if you want to split real and imaginary parts, right? Intuitively, you would expect that this is possible because all of computational algebraic geometry, every single step in every single subalgorithm, you essentially boils down to finding kernels and co-kernels of integer matrices. Why do I say that? It's because once you have polynomial systems, whatever you want to get can be expressed in terms of a basis of monomials. Once you have a basis of monomials, everything is then some kind of a matrix or tensor, and then every single step, whether you're doing non-exact sequence chasing or you want to find whatever you want to compute Betti numbers or Hodge numbers, every single step is finding co-kernels and co-kernels, kernels and co-kernels of integer matrices. So this is at least my intuition why every single problem in algebraic geometry is perfectly adaptable for machine learning. So it is very, everything here is over C, right? I will mention a little bit later. You're working over the complexes. All of that can be reduced to finding this problem, and therefore any conceivable problem in algebraic geometry, in computational algebraic geometry over the complex numbers, should in principle be very, very good and adaptable to a machine learning algorithm. So at least that's my intuition. Okay, everybody's happy with that? Okay, so I want to mention just in passing one last thing, which I recently did with my friend Shailesh Lau, and which is there is something called one-shot learning, which is this is actually very, very interesting. Remember, I've been talking about you can ask me how useful it is if you have to look into thousands of samples in order to extrapolate over tens of thousands, right? You need at least some kind of a training data, right? You want to have seen something like at least 20% or 40% of your data. I mean, it's already very good. But there is a paradigm in machine learning due to Li Feifei, and it's called one-shot learning. Is it possible to look at a single example in a category and then recognize everything else, right? So she had really good insight. She said, by the age of 6, every single child has learned something on the order of 10 to 30,000 object categories, right? And it is impossible by age of 6 that that kid will have sampled through 20% of 30,000 categories. So what is the child doing? So it's doing something called knowledge transfer, right? So for example, if the child has seen lots of horses and he has seen a single bird, just one example, and he would recognize that this bird, a chicken is closer to this bird rather than to the horse. So somehow there's some kind of knowledge transfer. So the paradigm of this is called one shot, or if it's a couple of cases, it's called few shot learning. So something I was trying with Shailesh and Zaid Zas, but Shailesh was he was a postdoc at Porto. He really took the lion's share in his work. And we were wondering whether it's possible, at least I was hoping, that the string landscape can be one-shot learned. Now, if that's possible, then this is a whole different paradigm, right? 10 to the 500 million of whatever, 10 to the 10 to the 5. If you just need to sample one single case to extrapolate over 10 to the 10 to the whatever, that would be great in terms of the vacuum degeneracy problems, in terms of in terms of what you actually need to do. Where do you sample, right? I said that we don't have a vacuum selection rule, we don't have a metric on the landscape, but this one-shot learning paradigm precisely does that by assigning a metric on the space of possible learned cases, and it does this by this thing called the Siamese neural network. I'm not going to get into details, but what it does is called Siamese, is that you have two inputs and it completely replicated. The features network here is the same as the features network here. And it does what's this called a contrastive loss. So what this means, you have a feature here and a feature here. You throw different pairs of features and it evaluates a similarity score, right? So, and it's a score of 0 when there's, if it thinks that input features are very, very similar. And if they're identical, it should be 0. So you try this to like SISSA3, which is 8,000. There's also a 4-dimensional version of SISSA called SISSA4, which is classified by this gentleman. And this is a much more respectable thing. So you need, this is about 1 million different cases. So even if you train this data set on the neural networks that I was talking about earlier on your laptop, we're now talking about on the order of minutes to hours, which is okay, not bad. I mean, but as opposed to hundreds of hours. If you want to do this proper algebraic geometry on this, it'll take exponential time. But in the categories that you want to categorize, some Hodge number in the 100,000 cases, this paradigm of the Siamese neural network in few-shot learning reduces the training to something like 0.6%, right? So you can see that it's actually doing very well on. So again, this is a matrix plot of your similarity. You want this to be diagonal, so that's why it's heavily, blue biased. And what's nice is that you can actually the encoding of this, it extrapolates a high-dimensional vector, right? This is a SISSA, remember, some matrix by some matrix. The similarity score is evaluated by Euclidean distance. So you can actually picture, so this is a picture of 1 million Clavier fourfolds in this data set. And it's colored by different Hodge number. So why does it do it? Because the Siamese network has recognized that by projection onto the sphere, it recognizes this optimal projection, which clusters similar Hodge numbers together. I love this diagram because this is a one look, and you say, well, this is 1 million manifolds, and you can explicitly see that the Hodge numbers cluster in different way. So I like it because we're inching towards interpretability. The reason that this whole thing works is because Hodge numbers tend to cluster by their own way. So we were able to uncover this by a Siamese network through this one-shot learning. And because it clustered, you only need a couple, on the order of hundreds out of hundreds of thousands samples, and you already knows what the nearby things are. So this is, I think this is very promising. You can do this. You don't need to look. You don't need to scan through hundreds of 10 to the 10 to the whatever samples in the string landscape, because the neural network will find features that will give a measure on the possible landscape. So this is we're inching towards this direction, which is, I think, is wonderful. In other words, we can't. So in the sense that I want to turn the question around, because it's very difficult to spot by the human eye what a measure on the landscape is, call it the geometric landscape or string theory or whatever landscape is, you need some kind of more sophisticated algorithm to do the pattern recognition in order to extract such a feature, right? So that's kind of nice. So any questions at this point? Or comments? Yeah. Yes.
Yeah, there is a question.
Yeah. Yes, please. Sorry, it's chatted or I can't see whether it's been chatted or.
No, he's got a, yeah, go ahead.
So I wanted to ask this. You were showing this particular algorithm, which is like doubly exponential and so on to find the Hodge numbers. And can we use this? Can we use machine learning in some way, or has this been done, where you can like use some insight from machine learning, which can improve the complexity of that algorithm, or like you change the algorithm somehow?
Absolutely. Yeah, so this is just, that's a very good question. So this, we are in the beginnings of this. So just to give a couple of examples, one thing I want to emphasize, 99.999% is not good enough, right? If you do reach 100%, then you have a very precise conjecture that your machine learning, that neural network is doing the correct thing. Then what you can do is to see what it's actually doing. Right, and so few things have been done. So in terms of computing cohomology, so there were papers by Andrei Konstantin, Andrei Lucas. So which is to sample through the space, because for line bundle cohomology, for example, a line bundles is specified by multi-degree, and you can plot this lattice of multi-degree, and from experience. What we've learned, and so we've been doing this. So this is a lot of work with Laura Anderson and James Gray and Andrei Konstantin. Myself with Andrei Lucas. We've been looking at just computing this bundle cohomology by brute force, and at the end of the day, you can actually end up plotting this. What region in this lattice are correct values for different types for cohomology, and there are no known analytic formulae, because the analytic formulae are actually very difficult until one starts to play with a machine learning algorithm to try to find the boundary. Once you found the boundary, you can and your training has reached 100%. You can actually make a conjecture. So wait a minute, instead of doing sequence chasing, what you've actually gotten, because you're secretly doing sequence chasing, what you've gotten is an analytic formula for cohomology. So that actually has been done. So this is sort of the beginning towards what I call, sort of the machine learning way of doing algebraic geometry, because here is an analytic formula you can actually write down. And they checked that against the sequence chasing, and they agreed completely. So that's kind of nice. So that's on one level. Another level is this Grobner basis computation. So this is done now by Mike Stillman, who he's one of the writers of Macaulay 2, and so Macaulay 2 is the sort of the state-of-the-art computational algebraic geometry algorithm. The bottleneck to the Grobner basis is the following problem. So if I gave you a linear system, and that's just the matrix, right? A Gaussian elimination, we know exactly what to do. You find the pivot, right? You eliminate until your matrix becomes upper diagonal, and then you're done. You've solved your linear system. So the Grobner basis is an exact analog of this, but in a tensor way, because you have to write down all the possible monomials. What it does is to find leading coefficients in some definition of ordering your monomials, and it tries to eliminate the leading coefficient. Right. So the Grobner basis for a linear system, if all of your polynomials, if your algebraic variety is defined only by degree 1 polynomials, that's exactly Gaussian elimination. But the complexity comes in because of this ordering of different monomials, you have to check all these different pairs amongst your system of definitions of polynomials to eliminate your leading coefficient, your leading monomial. And that's expensive because you have to do every possible pair of checking of this leading polynomial, and that's called the S pair. And you see where this is going, because if it's high degree and it's got lots of polynomials, this finding all possible pairs of this leading coefficient is going to be clearly exponential, because you're doing some combinatorics there. So what Mike Stillman did, and this was just a few months ago, he realized the bottleneck. I mean, he knows, right? Because he's the guy who wrote, he and Dan Grayson wrote Macaulay 2. instead of randomly, so what they were doing before was randomly sample through all possible what's called the S-pair comparison. And that's expensive. You can't do all of them, and you can't even do some of them. So they put in a machine learning algorithm, which very quickly converges to the optimal choice of these S-pairs, thereby reducing this double exponential algorithm to something much more manageable. So that's kind of nice. Does that answer your question?
Yes, he says in the chat box that it answers his question.
Yeah.
Okay.
So again, I encourage everybody to get into this, because this is, I mean, it's a low-hanging fruit, and we're just at the beginning. We're talking about just like last month, few months to a year, that there's this entire new paradigm of both conjecture formulation and computation reduction. Right? These are sort of the two reasons why we want to do this. So now I'm going to become a fanatic, right? Since I've made this very fanatical statement that all of algebraic geometry is a machine learning problem. And I hope I've convinced you, not just in terms of estimates, that's not in terms of just estimates to reduce landscape type of problems, but also in terms of precise conjecture formulation. And in addition, to find algorithms that help with complex computation. And now I'm going to become even more of a fanatic, which is how much of mathematics has this feature? Is algebraic geometry special, right? Or maybe it is because maybe we're just there because we're just dealing with kernels and co-kernels or matrices, and maybe that's what makes everything amenable. So I tried to explore various branches of mathematics to see whether it's machine learnable in the sense that I've defined here. So you can read this in this review from last year, and just sort of summarizing the kind of experiments that I've been doing with various on various fields of mathematics with various people. So let's start with with this, I said I'm a zealot now. I'm totally converted to this, right? We've seen that algebraic geometry C is a tensor manipulation image recognition problem. Well, then again, how much of mathematics is not that, right? So let's have a look. So give me indulge me for, I'm getting old, so you can indulge 5 minutes or maybe 2 minutes of my time in philosophy. Why am I asking this problem? Is because at the end of the day, how does one actually do mathematics, right? What are we actually doing? Well, one can go back to Russell and Whitehead, right? Their Principia Mathematica in the 1910s is a program that followed Leibniz and Frege to formally write down every single statement of mathematics, right? Of course, that program, it was killed by Gödel and Church and Turing because they showed that there are such sentences which are indecidable in mathematics. But I want to emphasize this did not, even though Gödel, Church, and Turing killed this Principia Mathematica program, it didn't actually prevent us to do what's now called the automated theorem proving paradigm. So in other words, the practicing mathematician does not worry about Gödel. What Gödel has shown is that sure, there exists some sentence in the far distant future of you to write down sentence by sentence. That is undecidable, but it's very rare. Most mathematical sentences are decidable and provable in a finite number of steps, and that's what Hilbert called the finitary method, because he believed that all of mathematics is finite, which is obviously not true anymore. But it's for practical purposes, it's finite enough. So just to give you a few highlights of this, even in 1956, these guys used the early, very early version of the computer called the Turing machine to actually prove certain subsets of Principia Mathematica. So that's pretty good. And that went on, sort of culminating in Verwirdsky's work in the last couple of years in trying to just write down all of the sentences of mathematics, right? And this program is called the ATP program. So I want to borrow a word from physics. I'm going to call this approach to mathematics the bottom-up approach, right? You build in sentences of mathematics step by step in its proof. And we know this is a very, very noble quest. And people like Kevin Buzzard at Imperial and Davenport have been based on the fact that there's an increasing number of proofs in mathematics which are simply no longer possible to be processed by humans. Namely, the most famous example is the four-color theorem. Now that was Czech. I mean, the four-color theorem proof in 1976 was a case-by-case check. They reduced the final number of cases to something like 50,000 graphs, and you need to check that they're four colorable, and then you just color them one by one. They were able to use the computer in the 1970s, which is pretty impressive. Again, the classification of finite groups was again impossible, not to be doable by the human mind. You need the computer to do it. So these guys in the ATP program have gotten to the point, they use what's called the Sinha project. You can access this online, where they're just literally writing down every single logical statement in mathematics and see how far it can go. And they're very optimistic. And they think within 10 years, the Sinha project, using the lean programming language, will prove every single statement in undergraduate level mathematics. In other words, you put in the logical axioms, 2 points define a line, 1 + 1 is 2, and you hit the return button, it will produce every single correct statement within undergraduate level mathematics in 10 years' time. And we'll see it. And they're very optimistic about this. They've been benchmarking this. So, and this is true in the sense that you will see the correct proofs, intermediate steps of all proofs of all of the statements. And as Szegedy from Google DeepMind has an even more extreme view. He extrapolated this is a simple extrapolation. The computers beat humans at chess in 1990s, beat humans at Go in 2018, and you will beat humans in proving theorems by 2030. So within our lifetime, we'll see this, and we will see theorems that are not provable. I'm hoping that maybe the Riemann hypothesis will fall into this category, but probably not. It's probably too hard. But a simple open conjectures should be provable by a computer by 2030, and we should be able to see that. So this is the bottom-up approach. What I'm proposing here in this set of lectures is sort of the top-down approach, again, to use a word from physics. Because the bottom-up is this formalistic approach, right? Logical sentences. What machine learning gives is intuition, right? Intuition from data. How would you actually do it? What is there to prove? What is the correct thing to calculate? So I like to use this analogy. The best neural network of the 18th, 19th century is the brain of Gauss, right? You can't beat that neural network. That was the best neural network that was available to humanity from the span of 18, 19 centuries, right? Because at the age of 16, he was able to look at this data. This is the plot of the number of prime numbers less than a given integer. And you can immediately say, oh, surely this is x over log x, because it's Gauss. And it had to wait 50 years before complex analysis was invented. And this theorem proved by Gauss. So what we're doing in this machine learning paradigm is to approximate this kind of intuition, right? And I think that is very much doable now because we have so much data of this type. We have gigabytes and not terabytes of mathematical data, right? And don't forget, even the most profound conjectures like the Birch-Swinnerton-Dyer conjecture in the 1960s, that was done because Birch and Swinnerton-Dyer had access to computers. This is one of the Millennium Prize problems. That's one of the deepest statements in number theory. But don't forget that these guys were just literally doing plots of ranks versus conductor size of elliptic curves. And they were able to spot their pattern exactly the way that Gauss was able to look at this. So now we have two different approaches of top-down and bottom-up mathematics. You can think of AlphaGo as top-down, right? Because it has seen a lot of human games. And you can think of AlphaZero as a bottom-up approach to the game of Go, because you're generating logical sentences. So the question I want to ask is, if I give you data of this type, or labeled data of this type, if I give you 100,000 cases, one, is there a pattern? Can a machine learning, or even a simple feed-forward neural network, can it see a pattern? Can it conjecture and then prove certain formulae? And we're already beginning to do this in the last couple of years now. And another thing that interests me is, having seen enough of hundreds of thousands of cases of such data, can the machine actually tell which branch of mathematics this data comes from? Is there an inherent structure to what we call mathematics, right? not just, I mean, by mathematics, I'm using this very loosely. It of course includes theoretical physics. If this data comes, if this data you feed it in, does it come from Feynman diagram scattering amplitudes, or does it come from proof gauge theories? No, whatever. Or does it come from like, a general relativity? I need this entire hierarchy of mathematics, right? So, yeah, I mean, in the sense that, if you detect outliers, sometimes it's even more interesting because it may give outliers to your structure, like sporadic groups and exceptional groups. Okay. So that's enough philosophy. I don't want to bore you with too much philosophy. And let's try to approach different problems in different branches of mathematics and see how well we do. Because, in the beginning, one might have imagined that algebraic geometry was very special because at its heart, it's about finding kernels, co-kernels of matrices. Or what about some other completely different branch of mathematics? So with Min-Young Kim, who's a very, very big name in number theory, so he suggested this problem to me. Take this crazy problem, right? We all know what a Latin square is, right? This is 1 to n. It's an n by n matrix, and you want to know repeats of rows and columns. So it's a Sudoku, right? So a Latin square is a Sudoku. He asked the question: every Cayley multiplication table, the multiplication table of every finite group, is a Sudoku. How many of them are actually, but not vice versa? So can you recognize a finite group just by looking at its Cayley table that is not just some random Sudoku, but it actually is a multiplication table? So now this problem is completely different in nature from algebraic geometry. This is a pure problem in algebra. There are theorems that do it, that you can check, but they're fairly expensive because you need to check every single combination. So we try, so the experiment here, what we did here is kind of interesting. You just plot the Cayley table, mix it up. I think we tried the first 100, first 1,000 groups. I can't remember the exact number, and then split it up and see. Again, this is a binary classification problem. I love binary classifiers. This is why I emphasize so much, because they're the simplest things to do. And what I'm reporting here is the accuracy and confidence, the naive precision and confidence. Well, and that's pretty damn good that your machine has, your neural net, your forward-feed neural network has absolutely no idea what it's doing. And yet it's recognizing what a finite group is to this level of confidence, right? Now, here is something that's totally crazy. What about a finite simple group? Can a neural network or a machine learning algorithm recognize the multiplication table of a simple group from a non-simple one? Now, this is an expensive thing to do. Normally, what you would do is to compute the character table of the group. Through some massage, you've got to find all its conjugacy classes, all of its finite dimensional representations, and then check through that character table whether something is simple or not. But now to just look at this plot of space, so we have n by n matrices, and I'm going to extrapolate this in the Euclidean space of n squared, Rn to the n squared. And that's what I was saying, that here my support vector machine is my favorite. So I use the support vector machine. And you can actually see a separating hypersurface that separated order by order the simple groups from the non-simple groups. So this is a proto-conjecture, right? This is a crazy way to do representation theory. It just says you plot the group in this high dimensional Euclidean space, a point cloud of groups. It's a proto-conjecture in the sense that I have no reason why to expect that such a hypersurface should exist. All I know is that it does exist, and I can tell you the equation of this hypersurface. But also, of course, it's an infinite dimensional space because of the infinite number of finite groups. So we can only check order by order. And the equation of this hyperplane changes order by order. But I don't know about how much. I haven't done the refined analysis of this. But this is like totally cool, right? Because you plot this and you can see that simple groups and non-simple groups actually separated in the way that a support vector machine would do, right? I mean, it's kind of cool. It's just exactly like this problem here, right? Here are the simple groups, here are the non-simple groups. Except here, the separating thing is not a linear hyperplane. If it were linear, it would be great because I can just tell you what that hyperplane is. It turns out it's a curved plane, but it is what it is. So that's why I say it's a proto-conjecture. I can give you the equation of that separating plane. I don't know what to do with it. Maybe it's an interesting way to do representation theory. So this was very encouraging because he said that algebraic geometry is not special, right? And that you can go into representation theory and many problems behaves just as well, right? So we're trying other things like, Lie groups, that's finite group, physicists love Lie groups. Can a machine learning algorithm, a simple feed-forward neural network, again, very simple, right? I mean, of course, in the infinite limit, of course, you know all of this thing should work. But we're talking about, 5 layers, no more, right? Which is, an under a minute training. To the weight decomposition problem to Lie groups, and that also worked to this high level of accuracies, right? So group theory and representation seems pretty good, right? What about combinatorics, right? What about if you take some finite set of finite graphs, and that's also a matrix manipulation problem. So I tried this like in 2020 with Yao. I'm very glad I got Yao into this. I was very surprised. This project started because Yao was asking me about generalizations of Ricci flat graphs. So this was his very specific problem. He wanted to generalize, what is his most famous for, which is, Clavier manifolds of Ricci flatness. He wants to see whether there's a discrete version of Ricci flatness, whether there's a notion for finite graphs which have a Ricci curvature that's finite. But as we were playing around, I said, well, why don't we try to search through these things through a machine learning algorithm? So we, again, wonderfully, such data is given. In fact, the Wolfram database of finite groups consists of I think something like 10,000 finite graphs. Certainly all the most famous ones are in there. And then use the same paradigm, 80-20 split or 20-80 split, train on some graph properties. Does the graph have cyclic? Does the graph have cycles? Is the graph planar? What is the genus of the graph? And you get this level of accuracies, averaged over neural networks, both vector machines, based classifiers. Just trying to do it. The one I want to emphasize here, this is interesting, right? Which is the problem of Hamilton cycle versus Euler cycle problems in combinatorics. So a Hamilton cycle in a finite graph is a cycle which traverses each vertex exactly once. An Euler cycle is one that traverses each edge exactly once. So the Euler cycle problem is the bridge of Königsberg problem. The Hamilton cycle problem is the traveling salesman problem. It is well known that this problem is NP hard. But it's also known that the Euler cycle problem it's polynomial. In fact, it was shown by Euler's student that there's an algorithm of solving the bridge of Königsberg problem in polynomial. They didn't phrase it in such a way, but now we understand what he was essentially doing is that problem can be solved in polynomial time. What is interesting is that both of these problems reached this level of accuracy in anything I could find. I couldn't do better than this. But they're of comparable size. So let me just quantify that a little bit. The Hamilton cycle problem, just because it's NP hard, has not prevented an entire field of research which stochastically solves the traveling salesman problem. Right? Finding such a path of the traveling salesman problem, it's impossibly difficult. It's NP. But if you want to get 90% of the time correct, then it's totally fine. And in fact, finding such a cycle problem of stochastically, they both reach this level of confidence, this level of precision and confidence, which is kind of interesting. Which says that this kind of search algorithms is inherently, it seems to me, inherently more difficult than problems in algebraic geometry and problems in representation theory. Okay, so why? I don't know. The word on the street is that learning permutations between matrices so far is a very difficult problem for any machine learning algorithm. Something as simple as that. But finding checking equivalence of permutations of matrices is the graph isomorphism problem, right? Because if you write down the adjacency matrix of a graph and you want to check whether these two graphs are isomorphic, you just check whether one adjacent matrix is the permutation of another. And that's hard, and that's an inherently hard problem. So it says, this shows that it's fairly difficult, but stochastically it does it to some degree. But once you put group structure, so we did actually, of course, enhance this data by showing, because the Kelly table is defined only up to permutation. You can recognize finite of simpleness of a group versus non-simpleness of a group using some standard machine learning algorithm. So okay, so this is not bad that you can still solve stochastically problems of such a nature. And you see where I'm going with this, right? I mean, if there is going to be a problem in mathematics that will be very, very difficult to do, it's got to be number theory, right? If I can start predicting properties of primes using the neural network, then I can probably break every bank in the world, and then you'll never see me again, right? I'll be in the Cayman Islands. So is that true? So I played with this game. First of all, can I predict the next prime? Well, there's no way I'm going to be able to do this, right? The fluctuation of this is just way too big. I can't possibly, well, yes, in principle, I can find a neural network that is of infinite size that'll probably do it, but that's going to be completely useless. But you certainly can't do this prediction for a very small neural network. 2 goes to 3, 2, 3 goes to 5. It's not going to do it. Okay, fine. So at least let me try something that's simpler and that's more manageable. Let's turn this into a binary classification problem. So how do I do that? Let me just line up all the odd integers, right? I want to use odd because, I don't want to bias it. If I put something in even, you don't just know it's not prime. So I want to put in all the odd integers, line them up, and I'm going to label, whenever it's a prime, I'm going to label 1. Whenever it's not prime, I'm going to label 0. So this is called the prime characteristic function. So now I have a whole string of ones and zeros. And now let me take what's called a sliding window. I take a vector of a length 100, and I'm just going to capture this 100. And then I'm going to see the next one. Is it 0 or 1? I'm going to move shift. Is it 0 and 1? Shift is a 0 and 1. So this creates for me a binary classification of 100, length 100 binary vectors. And I'm going to use my favorite things, such as support vector machines, or feed-forward neural networks, convolutional networks, or recurrence networks, to see how this prediction goes. I do 100,000 cases, 1 million cases. You may say, well, but surely the primes get rarer and rarer. There'll be more and more in zeros. So okay, fine. So I tried scaling according to x over log x because of the prime distribution. The prime number theorem tells me I can scale it, and then it becomes more uniform. It's pretty completely random, and and it does okay. Surprisingly, it wasn't doing completely crap, but it wasn't doing very, very well, right? Maybe it's doing 70% accuracy. This is nothing compared to algebraic geometry over C now, right? Because maybe it's recognizing, maybe it's kind of doing some very naive sieve method to recognize, which things are primes or not. But okay, it's hard to interpret, right? I love the black box nature of this. However, the following problem, which is much more interesting one, this is called Sarnak's challenge. So I do the same trick. Instead of labeling integers by the prime characteristic function, let me characterize it by so-called Liouville lambda function. So now I'm going to take all integers. So what's the Liouville lambda? It's essentially, I give you an integer. You tell me whether the number of prime factors of this integer up to multiplicity is an even or odd number. Okay, so I'm going to call even 1 and odd 0. And I'm going to use all numbers because it doesn't bias away anyway, even if I use even numbers, because I can just say the number, whether the number prime factors is even or odd. So I line this up. I train a binary classifier. I trained every single binary classifier that I can think of on God's green earth. The reason I try so hard on this problem is because Sarnak, who is a world's leading expert on analytic number theory, says that if you can find a pattern in the Liouville lambda function, it's inconceivable. It will be really, really, really difficult. Or if you do, I think it's willing to give you some money. I don't know. Don't quote me on this. Or I think that the stakes are very high if you can crack this problem. So interestingly, every neural network and every supportive action machine, every Bayes classifier I've ever tried, gave me precision 0.5 and confidence 0.000 something. So what does that mean? It means that it's not doing anything better than random guess, right? If I randomly guess this, I'm going to get 50% because I'm doing a binary classification. And that's fortified by the fact that my confusion matrix has chi-squared 0, essentially 0. I mean, the 1 is just that statistical fluctuation, meaning that my 2x2 confusion matrix is as non-diagonal as possible. So in other words, there is no pattern to the Liouville lambda function. It says there is a little bit of pattern to the prime characteristic function, but I could not find anything that does the Liouville lambda better. I'm not saying that you're not going to be able to find it, but I'm just saying I encourage everybody to try it. The code to do this, just modify the code that I've given you for weighted projective space. It's even shorter, right? There's no there's no fancy geometry or Hodge numbers. This is a binary classification of binary vectors, and the code you can just modify. I'm going to put the Mathematica code up, and you can modify that and just play with this problem. It's like totally crazy. It didn't break. It couldn't break even from random guess. Of course, I tried other random things like the collapse conjecture, which is again an open one. If you can see a pattern in collapse conjecture, you couldn't. I'm not saying that you might not, but I'd encourage you to try it. If you do find a pattern, then you'll be famous, right? I've just tried a dozen neural networks and run out of energy, but that's totally doable. So just to finish up, what was truly surprising for me was, okay, fine. So classical analytic number theory is not going to do very well, but the Birch-Swinnerton-Dyer conjecture does very well. So, or at least quantities of it. Features in arithmetic geometry, where you're working algebraic geometry not over C, but over some kind of finite field, or you're finding certain features over some Galois extensions of finite fields. So I was doing this again with my student, my PhD student at Hirst, and my master student Peterson on certain just enfant check. I won't bore you with this. And then I started working on like two card carrying, what Philip Candelas would call card carrying number theorists, and they taught me exactly the kind of experiments to check, which is fairly sophisticated stuff, all the way up to the Birch-Swinnerton-Dyer conjecture. And we were able to learn all of the quantities of BSD to very high precision, except what is commonly considered the hardest quantity of the of BSD, which is called the Tate-Schaffer-Age group. And that one we didn't do very well, as you would imagine, but it's still not randomly guessed. So hopefully, I mean, this is early days, right? I mean, this is all within the last year or so. We hope that this kind of approach once we start interpretability, will give insights towards attacking problems such as the Birch-Swinnerton-Dyer conjecture. So that's kind of fun. I think I'm out of time. So let me just summarize. It seems that I raised two levels of questions, which is, can machine learning help us with conjecture formulation and speeding up algorithms? So both of them, there's ample evidence now that this is true. And in addition, which is an extra, is that how much a machine learning algorithm struggles is indicative of an inherent hierarchy of mathematics that goes as the simplest thing you want to do, the simplest thing you can do is numerical analysis. The next one is algebraic geometry over the complex numbers, and surprisingly, arithmetic geometry. Luckily, string theory is somewhere over here. And the next level is algebra, and then combinatorics. So string theory is somewhere in between here. String theory problems tend to lie in here. And the hardest problem to machine learn, to actually extract patterns from, is, as you would imagine, classical analytic number theory, such as Sarnak's challenge. So since my time is up, I won't bore you. So there have been various volumes I've been editing just trying to push for this paradigm, not just to learn the machine and the string landscape, but you should really machine learn all of mathematics in sort of a complementary direction towards this ATP program of building up sentences of mathematics from top down. So indeed, I think this machine learning, this top-down approach is essentially in some way AI's answer to what human intuition is to machine learning. So I'm very glad, like just 2 months ago, there's a Google DeepMind collaboration which said the same thing. So so we're on the same page here. And so yeah, so my take-home lesson to all the students is that just go home and try your favorite problem. I will give you the mathematical code, and my students Ed and Jakan, who are really phenomenal, and they will teach you how to do all this stuff on TensorFlow if you don't like Mathematica. So I think my time's up, so I'll stop here and thank you.
So thanks very much, Yang, for a very interesting set of 3 lectures, very thought-provoking. And of course, I'm pretty sure the students will go away and learn machine learning more as well. So are there any questions? Yeah, so there's a question in the chat box by Reiko Liu, who's asking, by the approximation theorems, could the neural network learn these problems, say the Liouville lambda function, by increasing the layers and widths?
Yes. I haven't tried it, but I think that's something you should try, is to increase the depth and width, and I think you should see the precision increase a little bit. And I think in the infinite limit, I think you will get 100% accuracy. I think as you must, but that's not very useful because it's just at that point it becomes completely uninterpretable. What I'm hoping for is that a finite depth one would do it, and then you can start interpreting why the Liouville lambda function is or at all has any patterns.
Okay, any other questions?
Hello.
Yeah.
Look, go ahead.
Yes. So in all these different kind of mathematical problems, you said, let us say, like in this finite simple group classification.
Yes.
Do we understand, like what are the cases where it fails? Like when you say 80%, 90%, like what is specially, what is mathematically special about the cases where they fail?
Yeah, that's a very good question. And I think that is the way to do it. If you want to find out exactly what is breaking your algorithm, you should, or if you want any interpretability, the way to go is to start with the cases where it fails and why it fails. That certainly is. I haven't done detailed analysis on this. I think it will be very difficult because, because that does actually require a lot of human intuition. Why this? It's very hard to spot, right? Because here's a matrix that worked, and this is a matrix that didn't work. Why is this one? And I guess if you sample enough number of times and you can home in on the case that's consistently failing, then maybe you can even use some kind of a meta-analysis to find establish another neural network that finds out what is at fault here, right? Why that one is failing. But that is certainly the correct way to go, is to find out these exceptional cases.
No, for example, like let us say if I take all the cases where it fails, okay.
Yes.
And then I look for something which tries to predict, seeing a table, whether it will fail or not. How well will I do?
I don't know. You should try it. I don't know. Good question. I don't know. Yeah.
Okay. Like, is failure predictable? That's what I'm trying to.
I can't answer that in general, but that's a good question. I mean, that definitely you should try something like that. I mean, try 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 a data set that you're most comfortable with. Maybe even try a data set that where certain things would fail, and then see whether it detects that. Yeah.
Thank you.
Yeah, naively it would seem like if you were trying to say take the input from Navier-Stokes equation or some nonlinear differential equation and use a neural network to predict, that would be quite hard. I mean, is that
I think that would be, I think that's actually okay, because if you just want to find some, numerical solutions, I think that should be very easy. I guess that the hard part is there to prove the existence of this, in some, in technical terms. I think that's the hard bit. But I think numerical solutions of PDEs now there's a very active field of finding, using machine learning to very quickly converge on numerical solutions to PDEs. There's a big field in that now.
I see.
And I'm not sure how much distinct, whether, certain, Navier-Stokes is harder than, like some other elliptic thing. I don't know the statuses. Maybe not, because it's just purely because, the reason I say so is because the Hamilton cycle problem was just as hard as Euler cycle. So in terms of complexity, you can't get it because there's a lot of stochastic stuff in there.
Very nice. So this book that you flashed, which is about machine learning theoretical physics, and I mean it was too quick. I forgot to make a note of it. But is that out, or is that you're on the process of writing it?
Oh, it's out. It's out in the summer. It's Springer lecture notes. And I try to make it as pedagogical as possible, and I actually included code in there.
Okay.
Yeah, all of the code in Macaulay 2, Sage Math, and Mathematica, and TensorFlow. Even TensorFlow, I put in all the codes in appendices.
Okay.
So people can just copy and paste and run it. And I can certainly give you this demo package. I wrote that demo page that on Mathematica. I wrote that up last night, and that I can just upload. I can just email it to you together with the data.
Great. No, that'll be very useful. Yeah. So there's a question in the chat box. Feel free to take it as well. Could you say a few words on the applications of machine learning methods to the conformal bootstrap program?
I was playing with that with Hengyu Chen and Shailesh Lal, but because I know very little about, I had to. By the time these guys taught me about the conformal bootstrap problem, I think there's a paper out already on it, on machine learning bootstrap. And I was like, oh well, it's entirely my fault because I actually learned this. So I think it's let me see. Let me just try to find. Yeah, so there are. So we can you see my oh sorry, I need to. I'm going to just copy and paste. So at least I'm looking for here it is. I'm looking for my chat now. Here's the chat. Chat. Oh, there we go. Can you say so? So there are these 3 problem papers. So so with Hengyu and Shailesh and Zaid, we tried the very first step, which is to machine learn whether a data set has conformal symmetry. And then, then these guys, so obviously what you need to do. And then this paper by Gegli, Cantor, and Nyachos, I think they try to reinforcement learn the conformal bootstrap, which I think is just a simplex optimization problem. I think the entirety of the conformal bootstrap is some kind of simplex optimization now, I think, because of this numerical bootstrap. And these guys obviously used a very nice technique, which is reinforcement learning, to how to map, how to speed up that process.
Right. Okay. Any other questions? Anybody? Any comments?
Sorry, I had one more question.
Yeah, please.
This about one of the statements that you had made in your slides about Seiberg duality and so on and so forth in terms of figures.
Yes.
In general, like if I have 2 kind of structures, which I think are dual, like say mathematical structures.
Yes.
Let's say both are given by some ADE classification or something.
Yes.
Say McKay correspondence, something. And like, is there a way that machine learning will tell me that there is some correspondence like that if I give the data? I mean, like, is that even can it even be formulated? Like, can it discover McKay correspondence? Let's say if I just give it, both the, some finite the subgroups.
Yeah, I think that's going to be a higher level, because spotting the ADE pattern that exists in both sides of McKay correspondence would be, you could find many things that has that ADE pattern, but then to know that you have to do this tensor of the irreducible representation, the two-dimensional irreducible representation to get the graph. I mean, that's kind of Mackay's genius. In principle, I think if you talk to people like Tegmark and increasingly fanatics like myself, I think we will be able to do that. Once we have enough mathematical data, it will start to try all of the tricks of the trade and then start extrapolating this. I think that is doable, but not in an immediate future.
Okay. And could you repeat what is the issue there? Why?
Is it because I can do pattern spot? I can say, here's an ADE pattern in the classification of groups. Here's an ADE pattern in the classification in the subgroups of discrete subgroups of SU2. Here's an ADE pattern in the classification of Lie groups. If I just looked at it, the machine may be able to pick that up. But in order to go one more step and say, how are these two related? Because Mackay needed the two tensor decomposition and recognize that the AIJ, the coefficient, the Clebsch-Gordon coefficient of the decomposition is exactly the Cartan matrix of the Lie group of the Lie algebra. That's kind of where the hell did that come from? Right? That's another level. But I think we're getting there. So just to give an example. This is actually really, really cool. In 2019, a collaboration was published in Nature where material scientists, what these guys did was to take all of the abstracts of all of the papers ever published in the history of material science. So it's about 4 million abstracts. And material science, you can imagine, is, in terms of information theoretic complexity, is much simpler than mathematics. In material science, is like, here's a material A, here's material B, they're likely to react in the chemical way, and it's used for C. Like, all of the abstracts in that is of this type. So what they did was to do natural language process of these abstracts, and they were able to not just machine learn this, and they were able to extract hundreds of new chemical reactions that never appeared in the literature before. So just by the linguistics of the abstract, they were able to say, you should probably go and check this, and it'll probably do better. And now they measured this over the last few years, and they actually found hundreds of new reactions, chemical reactions, that were actually better. And that's why it's a Nature. I was very saddened by this paper, because right after 2017, one of the first things I wanted to do is machine learn the archive, right? And I wrote a fun paper with Vishnu Chajala and Brent Nelson, and of course this is much more sophisticated, but essentially it's the same technique, right? And then we were trying to get I can show you this. This is really fun. Like I can show you this. The slides. Let me share this again. So here, this one, right? So what we did was we didn't have the technology to try the abstracts because it was just too much. But we took the 2.3, whatever, I think 2 point something million titles of all of the sections of HEP-TH, GRQC, HEP-PH. I ran through it, the word-to-vec neural network, which is essentially, I mean, I won't get into the details, but this is what got Mikolov famous. The reason that Mikolov was bought over by Google in 2013 was that he realized this contextual data of sentences in natural language processing allowed you to see So what essentially, so you know this guy's an ex-physicist, right? He's writing on partition functions. He's basically saying, okay, take some sample data. So here is the point cloud data of the most likely occurring words in these 5 different sections, right? So HAP-TH's most common word is model. HAP-PH is also model. So you can't really distinguish it. But is there syntax that distinguishes HAP-TH from HAP-PH? So then what Mikolov did in 2013, way back when, was just realize, well, you can try to find distance between words to see what, not only what's likely a word is to appear in terms of frequency, but also how likely a word is adjacent and next to adjacent and next to adjacent to another word. So that gives you what context the word means. So we tried this algorithm to the titles of all of these sections by mapping. So this neural network, just like the, kind of like Siamese network, it maps the space of your words to a vector space, and then each sentence is a point in the vector space. Oh, sorry, each word is then a point in this vector space. What is interesting is that you can now use a vector space. You can add and subtract, right? So when he did this to Google documents in 2013, he was able to do this to 1 billion documents. And he was able to syntactically find things like a man plus a king is equal to a woman plus a what. And it found the word that's most likely to fill that gap because of the proximity in vector space is the word queen. And it's fantastic, right? That it showed that this algorithm, this word-to-vec algorithm, this neural network, is able to detect what we call, understanding. And in some sense, this is not how Google works, right? Because, when they do sentence prediction, when you type Google, it starts to complete your sentences. It precisely has built-in word-to-vec. Of course, it's been, this has been improved a lot since 2013, but the basic structure is something like this. So we tried with HAP-TH, and we're able to find sentences like this. This is awesome, right? The word bosonic plus string theory is open string. My favorite one is this one. The word string theory plus Calabi-Yau is M theory plus what? And you search, the most likely word is G2. That's fantastic. Of course, I'm cheating here because I've given you my favorite ones, and there's a lot of nonsense that didn't exist. So in that context, well, what I was hoping at the time before we ran out of steam was to really push for this and say, well, can we make the next discovery in string theory by this? And I think it's actually possible. If you took all of HAP-TH, because that's what we do, right? I mean, what do researchers do now, right? We don't have time to read through all papers. We look at the title, the abstract, the introduction, and the conclusion. If we can get those texts in and then feed this into word-to-vec, it's probably very, very fiddly. Once you do it, I mean, if somebody has the energy to do this, I would love to collaborate. And then just like that paper with material science, I think it's not inconceivable that we may predict what the next breakthrough in string theory might be. So that's just from syntax. I think that's doable. So in that sense, you can just keep on going with this, right? Mackay correspondence in mathematics is something like this. If you somehow regularized all of the symbols in mathematics of every single text in the history of mathematics, it's not very much, right? It's at most 1 terabyte of data. And that terabyte should be fed into something like a syntax detector like this, a natural language processor unit like this. And then it is not inconceivable that it will, this is intuition, right? This is exactly what I'm talking about. This kind of neural network is exactly the complementary bit to the ATP program, which try to build sentences of mathematics from scratch. But this will give you what the syntax of what we call theory is. And I think it will start to make connections between different fields that we've never seen before.
Thank you.
Okay, so I think we don't have any further questions. So let's thank Yang for a very nice set of lectures. And there will be Yang's tutorial on given by students on Sunday. There is a question. Okay, hang on a second. Professor, can you please join the Slack channel? We all are there, and it would be easy for discussions even after the lectures get over.
Yes.
Well, Dr. Yang
The only problem is I need to travel to get to my office. Can we do that in a couple of hours time and then join that slide, or do you want to do it now?
Yeah, I guess they will post questions and then you can answer them at your leisure. So there is no.
So I've never used Slack. I'm not exactly sure what that platform is. So I have a link to it. So what do? I just log in once I.
Yeah. So you have to log in, and then there are various groups. So there is a group created for you as well for your lectures, and then they can ask you questions in that group, and then depending on you can answer them at your convenience. So there is no immediate rush.
Oh, okay. Good. Okay. Good. Yeah.
Okay. Yang, thanks very much.
Thank you very much for having me, and I hope next time I will see you all in person.
Yes, absolutely. Bye-bye.